I think we can start the introduction. So this nice presentation will be given by Nirmalia and Vinayak from the Jaguar Land Rover team, and they will tell us about FEA modeling of eddy current losses and permanent magnet of PMSM motor for EV traction application. So before letting Nirmalia and Vinayak starting their presentation, I would like to say some words about them. So Nirmalia Panigrahi is a graduate mechanical engineer working for Jaguar Land Rover in India. He is working with design of electric machines in JLR electric powertrain since September 2020. He graduated with Bachelor Tech in Mechanical Engineering from Indian Institute of Technology in Kharagpur in 2020. And Vinayak Gupta is a graduate mechanical engineer working for Jaguar Land Rover in India. He's working with the design of electric machine in Jaguar Land Rover electric powertrain since September 2020. He is graduated also with a BTech in mechanical engineering from the Indian Institute of Technology of Bombay in 2020. So thank you, Nirmalia Vinayak, for joining us for this user conference. I will let you share your screen now. And in the meantime, I just want to remind the attendees that, as usual, you can ask questions during the presentation anytime, and we will collect all the questions to go through them after Nirmalia's and Vinayak's presentation.
Yeah, thanks a lot for that introduction, Corentin.
Are you able to share your screen or?
Yeah, I am sharing my screen now.
Yeah, we can see your screen.
Okay. Yeah. Thanks, Corentin, again for the introduction. I think we will start now.
Yeah. So hello everyone. This is Vinayak Gupta, and here with me is my colleague Nirmalia Panigrahi. We are here from Jaguar Land Rover in the JMAG Users Conference. Today we'll be presenting our work on the FEA modeling of eddy current losses in permanent magnets of a permanent magnet synchronous motor, especially for the EV traction applications.
Now, if we take a look at the last decade, industries have been revolutionized. With every passing day, there is a pressing need for new, cleaner and greener fuels. Robotics has swarmed into other industries, transforming the way we thought about manufacturing, assembly, and process line techniques. However, the most significant impact has been of e-machines in the mobility sector. Just let's take a look at the numbers. In 2010, we were selling around 10,000 of units. Today, we sell 2 million electric vehicles. And in the next decade, this number is going to rise into 25 millions. Not even the numbers, the trend in the number of patents that are filed every year in the field of electric vehicle, hybrid electric vehicle, and fuel cell electric vehicles, there is a meteoric rise. Therefore, we are convinced that this part of the century belongs to e-machines. We at Jaguar Land Rover have reimagined our design thinking to build a sustainability-rich, unique customer experience with a positive societal impact. We want to embark on a net zero carbon business by 2040, and from 2025, we want to build an all-electric fleet to unlock the unique potential of Jaguar Land Rover.
The implication of all these factors is huge volumes and competitiveness for the e-machines. Thus, factors such as the performance, showing the torques, speed, and operating conditions, the efficiency, showing the losses occurring in the e-machine, the reliability and sustainability of the e-machines become vital. Considering the global scale, Even a small amount of savings in the e-machines can, over the huge global scale, result in massive savings. From the perspective of a single machine, the reduction in losses can result in better efficiency, higher torque density, and high power density. One type of losses that occur in the e-machine is the electromagnetic losses. The electromagnetic losses occurs in regions such as the magnet, rotor, and stator. The core losses, that is, the losses occurring in the rotor and stator, in general occupy the highest proportion of the total losses. There also has been a lot of research as well as various methods developed to calculate the core losses, such as the modified Steinmetz method, the Bertotti method, and the modified Bertotti method. The losses are again of three types: the eddy losses, the hysteresis losses, and the copper losses. The eddy losses is the induced current due to the fluctuation of the magnetic field. The hysteresis loss is produced due to the self-magnetization fluctuation in the external magnetic field. The copper loss, as the name suggests, is the losses occurring in the copper windings. This presentation is scoped only towards the magnet eddy losses, the reason for that being that even though it occupies a smaller proportion of total loss, we already have well-developed methods for the calculation of core losses, and the magnet eddy losses does become higher in certain operating conditions. So today, we will be developing a model as realistically as possible and then estimating and reducing the magnet eddy losses through simulations in the JMAG.
Now, as Binayak explained here, when we come to magnets, the hysteresis losses and the eddy losses are two of the most important losses we should be looking at. Now, specifically in EV traction applications, since our magnet parts are not exposed to repeated magnetization and demagnetization cycles, the hysteresis losses are not much prominent. However, there are current loops passing through the magnet parts and there are eddy losses. Therefore, we believe any activity which focuses spatially on magnets and wants to measure its losses must actually focus a lot on these eddy losses. Now, a brief background of what eddy losses are. To start with, these are extremely relevant at high speed operating points and when the carrier frequency of the inverters powering the stator coils is high. Now coming to the effects. Since it's due to the current loops formed and the induction heating, eddy losses tend to raise the temperature of the magnet parts, thus bringing in the risk of a thermal demagnetization. Again, since a part of the input power is lost in terms of heat, there is a reduced efficiency. Therefore, we now have to go back and increase dimensions of the machine, thereby reducing the torque density. Coming to the analytical side of things, there are majorly two components of the eddy losses. First is independent on the stator excitation, called the no-load component. This depends a lot on the stator geometry, specifically the reluctance variation due to the stator slot openings. The other component, which is due to the current flowing in the stator coils, is mostly contributed by the spatio-temporal variation of the magnetomotive force and its harmonics. Moving forward.
So having explored the eddy losses, their origin and their effects, we now move on to develop the model for simulations in the JMAG designer. So the model that we chose for this simulation is a radial flux permanent magnet synchronous motor. It has 48 slots and 8 poles. It has a full pitched winding. It also has a double V-shaped magnet rotor topology, as can be seen in the figure. It has 7 axial stacks measuring 180 mm axially in total. The important point to note here is that this model does not contain any skew. Because it does not contain any skew, the 7 stacks model exhibits an axial symmetry about each stack. Thus, in order to reduce the computation time, we use this symmetry factor to reduce the 7 stacks to just a single stack. Now, as this single stack itself has a radial symmetry, so we reduce the single stack 8 poles to just a single stack, one pole over which we will run our simulation once we have completely defined the model.
We took a look at the design of our rotor laminations and the stator laminations. Now let's see what kind of materials we used for the simulation. To start with the stator and the rotor. In each of them, we used an alloy steel of grade AM235-35A. Now, to simulate the effect of laminated sheets of alloy steel, we used the stacking factor of 95%. Coming to windings, we used pure copper. Lastly, in magnets, we used magnets of grade N42UH, assuming an operating temperature of 80 degrees Celsius. Other important electrical properties of these materials have been listed down in this slide. Going forward.
So one of the important conditions while evaluating the magnet eddy losses using FEA is the insulation boundary condition. The figures shown here represents the magnet configuration of a single stack, single pole, because this is the model over which we will run our simulation and then scale the result for the whole 7 stacks and 8 poles. On the left-hand side, we see that the magnets does not have the insulation boundary condition applied over the ends. This means that the magnets of 2 separate stacks are not electrically insulated to each other. Thus, when the eddy currents are induced into the magnets, the eddy loops formed in the magnets will be formed throughout the 7 stacks as a single piece. This means higher cross-sectional area, higher magnetic flux through it, and thus higher induced magnetic eddy currents, and thus higher magnet eddy losses. On the right-hand side, we see that the magnets have the insulation boundary condition applied over it. This again means that the magnets of 2 separate stacks are now electrically insulated to each other. Thus, when the eddy currents are induced into the magnets, the eddy loops will be confined only to one stack, thus reducing the cross-sectional area, reducing the magnetic flux through it, and so reducing the eddy currents within the magnets and thus lower magnet eddy losses. This means that the insulation boundary condition is a must while defining the model, because this makes your model as close to the real conditions.
As of now, we have taken a look at the design, the materials, and even some best practices concerning boundary conditions. Now, let's take our first look at the results. Now, here we have tried to see how these losses vary over the speed range. For that, we have selected 3 operating points. One, at a base speed range of 5,500 rotations per minute. Second, at a mid-speed range of 10,000 rotations per minute, and finally, a max speed range of 15,000 rotations per minute. In each of these speeds, we are exciting the coils to a current of around 350 amperes RMS and have chosen an advance angle which optimizes the torque for the given speed and current conditions. Now, you can see the losses listed in the last column. We see that at the base speed operating point, the losses are merely 14.2 watts. However, this saw a massive jump when we move into the mid-speed range, going to roughly around 106 watts. And there is again a significant rise when we move from the mid-speed to the max speed range. Overall, if we compare the base speed with the max speed, we see almost a factor of 12 jump in the magnet eddy losses reported. Therefore, we believe that any exercise which focuses on magnet eddy losses must take into account these high speed operating points. Now coming below, I have tried to represent the magnet parts in a rotor geometry and a figure alongside which shows what proportion of losses comes from each of these magnets. Here we observe that as we move higher up in the speed ranges, the proportion of losses coming from the bigger magnets tends to increase. Therefore, another important conclusion from this slide is that if we want to reduce the magnet eddy losses, we should concentrate on the larger magnet parts and effectively work on a strategy which can help us achieve that. In the next slide, I would like to show you a brief demonstration of how the current density varies in the magnet parts at the 3 speed ranges. Also, I've included a vector plot so that you can identify the current loops forming in this magnet parts. Here, as you can see, at the max speed, there is an unusually high current density, which explains why we saw such bigger losses at those speed operating points. Moving forward.
After seeing the results of the unsegmented magnets, we now see how can we reduce the magnet eddy losses. So one of the way to reduce the magnet eddy losses can be through the change of materials, or like choosing a material which has higher electrical resistivity, or choosing a material which has lower magnetic permeability, or you can operate the e-machine at a less aggressive operating condition. That means a lower stator current. However, one of the ways in which we can reduce the magnet eddy losses and still need not worry about the operating condition or the change of material is through the segmentation of magnets. Again, the figures shown here represents the magnet configuration of a single stack, single pole. On the left-hand side, we see the unsegmented magnets. The unsegmented here means that no further segmentation has been performed over the magnets of a single stack. This means that the insulation boundary condition over the magnet ends here still holds. And the result for this type of configuration, Nirmalya just explained. So in order to go ahead with the study of magnet eddy current reduction through the segmentation of magnets, we perform two types of segmentation, the axial segmentation and the radial segmentation. In the middle figure, we see the axially segmented magnets. Here, all the 4 magnets have been axially segmented to result into 8 magnets. On the right-hand side is the radially segmented magnets, where the larger magnets have been radially segmented, again, as explained by Nirmalya, because the larger magnets create higher eddy losses. So having defined the segmentation of magnets in the axial and radial direction, we now will solve both of these models and then compare the results with the unsegmented and among all of them.
Exactly, Vinayak. Now, in this slide, we build upon the results that we had collected in our last set of experiments. Here again, you can see we have the 3 speed ranges, the base speed, mid speed, and the max speed ranges, and have maintained the operating conditions having the exactly same current advance angle and same torque output as always. Now, here we concentrate on how effectively are our strategies of magnet segmentation working out. Let's start with it. At the base speed, we see that both axial and radial segmentation are giving us a 40% reduction in losses. This is 40% reduction in losses. Again, at the mid-speed range, the reduction in losses is in the higher 30s side. When we move into the max speed ranges, the reduction in losses comes to the early 30s. Another conclusion from here is that radial segmentation tends to become more and more powerful as we move higher up in the speed ranges. As you can see, at the mid speed, it is nearly 3% better than axially segmented magnet parts. And at the max speed, it tends to become nearly 5% better. Therefore, one conclusion from here is that overall in the complete operating range, we can expect around a 35% reduction in losses from magnet segmentation. This is roughly 1/3 of the losses that we saw in the unsegmented magnet parts. And that radial segmentation tends to become more useful and advantageous as we move high up in the speed ranges. Below, I've tried to represent how the losses vary over time for 3 of the operating speeds, including 3 of our segmentation strategies. That is, one going with no segmentation, the unsegmented ones, then with axial segmentation, and with radial segmentation. Now we will move forward.
So we saw how to reduce the magnet eddy losses. But how can we make the model itself very close to the real conditions? So till now, the simulations that we performed were over a single stack, single pole, which does not has any skew which in general is a very standard practice in the e-machine industry, owing to its benefits of low torque ripple and better engaged performance. So in order to develop the model as really as, hello?
Yeah,
Yeah. So in order to develop the model as realistically as possible, we develop a model which has a skewing built into it within every stack. So this model here also possesses some symmetries. One of the symmetry, as can be seen, is the radial symmetry, and thus we use only a single pole for the simulation. However, actually, as we said, this model has a skewing which can be seen in the figure. There still exists one level of axial symmetry, which is exactly through the middle of the whole e-machine. So as we see, there are 7 stacks and it can be sliced through in between to result in 3.5 stacks. And then we perform the simulation over those 3.5 stacks and a single pole. This model also has the other similar conditions applied to it as the single stack, single pole had. That means it has the insulation boundary condition applied over the magnet ends. Again, this magnets are not actually or radially segmented. We can call it unsegmented magnets with insulation boundary condition. This has a semi-automatic mesh development. So this completely defines our model. And now, having defined the model, we solve it and move towards its results. So as we can see, the skewed model has also been simulated over the same operating points. That is, it has been simulated over the base speed, 5,500, mid speed, and the max speed with the same current and advanced angle. Coming to the torque produced, we see a maximum, we see that the variation is within 5%. For the base speed, we see that the torque is lower, but for the max speed, we see that the torque is higher. So according to the simulations that we have performed, we see that it's not that the 3D, that it's not that the skewed model produces results either produces lower results or higher results. It just produces them similar to what the no skew produced, but the maximum difference is within 5%. Now we come towards the magnet losses. The magnet losses are even more similar, as we see the 13.5 watt, 14.2 watts for the base speed, the 105, 106, 171, 169. Even at the maximum speed, when the magnet eddy losses are the highest, we see the maximum difference of only 2 watts, which means that the magnet losses are pretty similar. Of course, the computation time here was a lot different. We can conclude here that because the computation time taken by no skew model is 10 times better than the computation time taken by the skewed model, and at the same time producing similar results, we can say that the no skewed, that the single stack and a single pole model can be used for the simulation to get the results.
Well, now I would like to give an overview of this complete journey we had over this seminar talk. First of all, we started with basic designs, materials, and boundary conditions. The first result we saw was the variation due to operating speed. What we observed there is that at high speed operating points, we have significantly higher magnet eddy losses reported. We looked a bit into how these losses were divided among the magnet, and we saw larger magnets were giving proportionally higher losses. Also, it was important there to see that from base speed to max speed, there was almost a 12-factor rise in the losses produced. Then we moved into our strategy of magnet segmentation. In magnet segmentation, we compared results between 3 strategies. First, leaving them unsegmented. second, axially segmenting them, and third, radially segmenting them. We saw overall there was roughly around 35%, which implies one third of reduction in losses uh, while implementing the strategy of magnet segmentation. Also, this we observed that although slightly radial segmentation tends to become more advantageous as we move into the mid speed and the max speed ranges, roughly around a 5% difference, but radial segmentation can be seen as a better strategy than axial segmentation in our study. Finally, in the last leg of our study, we saw three-dimensional modeling to include skew. The aim here was to see if our simplified model was under enough confidence as a fully developed model including skew would be. We saw that it indeed happens. Our talk results were within a variation of 5% and our magnet eddy losses were roughly 1 or 2 words here and there. Therefore, we believe that having a one stack, one pole simulation and using these results is a highly optimized case and can be used for results with considerable confidence. With this, we sum up our study on the eddy losses from magnet parts from a permanent magnet synchronous motor, especially for EV traction applications. With this, I would like to extend my gratitude to our team at Jaguar Land Rover who helped us bring this presentation from scratch, our colleagues at Power System Solutions who helped us whenever we had doubt, and for giving us this wonderful opportunity. Finally, I would like to thank all attendees of this seminar for investing your time with us. I hope it was worth it. With this, I believe we will take some questions here.
Thank you, guys. Thank you, Nirmalia. Thank you, Vinayak, for your very nice presentation. It was really, really interesting. We already have some question, which is good. So we've got first question that you can find on the Q&A panel in Zoom. During radial segmentation of the magnets, is the junction of the magnets guaranteed, or is there a set between the parts?
Okay, I would like to take up this question. So from modeling side of things, when we radially segmented the magnets, which was mostly the larger magnets, magnets 1 and 4 in our nomenclature, as I showed you, uh, we built the geometry and then placed an insulation boundary condition between both of those magnets so that the current loops between the magnets do not cross into one another, and we ensured this while going through the post processing that none of the current loops from one segment of the magnet moved into the other magnet. In that way, we were certainly confident that the segmentation strategy that we were trying to implement had been implemented with certain success, and we believe our results also showed the very same.
Thank you. Next question in the chat panel of Zoom. Thank you for interesting presentation. On slide 13, the skewing involve dumping on the induced voltage and on the maximum torque amplitude as well. I think this is from your presentation. Have you tried? The question is, have you tried to increase the current in order to keep the same torque amplitude with the skewed rotor? And what would be the impact on the eddy currents in the magnets because of this current increasing?
As of our exercises involved, I believe we kept the similar current levels. I am not, I believe, if Vinayak, you have an idea regarding the second question, which goes on the impact of eddy currents. We believe with rise in current, there should be certain increase in eddy current levels and therefore
Yes,
more
yes, there
losses.
will be.
Yeah,
Uh,
but yeah, go on.
the eddy currents will increase the magnetic flux through it. And so, of course, the induced eddy currents will increase because of the increased magnetic flux through it. Yeah, that will be the second part of the question.
I would like to add that for this purpose, they have not done any study on increased current. So the second part of the question is not exactly relevant because we have not done that study. What is the impact of current increasing?
Thank you, Fasil, for completing this answer. Next question is, do the conclusion about the direction of about the direction of the magnetization can be generalized with machine with different dimension and segment actual length?
Yeah, I believe the question here is about generalization. And I think, yeah, it's a very good question in the sense that it asks about if generalization of one particular strategy is useful. We believe, of course, these eddy losses that we see are a function of the dimensions and the magnitude of the loop formed. Therefore, it essentially depends on what scale of dimensions the magnet are after the segmentation. However, in our exercise, since we tried to keep the segmentation in such a level that there would not be much difference between axial and radial segmentation, we believe this result set in particular, given these dimensions of the magnets that we used, could be generalized. However, we believe with varying magnet sizes, unless there is a proper study done with respect to segmentation and dimensions of the magnet, such a result cannot be exactly confirmed in sense of the percentages that we saw. Do you like to add something?
Yeah, I think that was absolutely correct. So we cannot directly generalize everything. It would depend on the dimensions of the magnets after the segmentation. Yeah.
Okay, thank you. Next question is, what about incorporating both radial and axial segmentation simultaneously? Will this affect the flux linkage?
Okay, the variation on flux linkage, which should have been reflected in the torque, I believe we did not see much of a change there. However, we kept in mind that although multiple and heavy scale segmentation is possible in theory, it would actually be complicated when manufacturing standards are put into e-machine development. And therefore we tried to limit our strategy to having mostly two segments, and that was our understanding behind going on a single segmentation and not including multiple segmentation within one stack of rotor. And these are valid questions, I believe. And as I said before, all of these would involve. I am sure it's just further scaling of the kind of work we did, and I think these results can be easily obtained using JMAG.
Thank you. So for the next question, I will copy paste it on the chat so you can read it as well. How much I think you have already maybe answered this question during your presentation, but maybe you can give a small reminder. How much percentage approximatively is the contribution of the eddy current losses in the total machine loss? Segmentation of PM can be used to reduce eddy current loss. I think this is a comment.
Nirmala, do you remember the value?
Yeah, I think I have a representation.
Yeah.
I would try to go back to that. Just give me a second. Yeah. So here exactly we borrowed this paper from Yamazaki Kasumi and Makamoto Tanida, where they were investigating into iron losses in rotating machines. And here you can see on their various set of experiments how they quantified how much of losses actually belonged into different parts of the e-machine. And here we believe we get a proportional sense of how much of the measured losses from machines can be contributed to magnet eddy losses. I do not have exact figures, but I believe it's pictorially shows us how much of this
About
actually,
10% around.
yeah, we could say roughly 1/10 of this losses. But we believe when we consider magnets alone and want to optimize the losses for magnets, mostly because of the temperature rise and variance, the effective risk of demagnetization and all. That is why we considered eddy losses as primary sources of those, and had a full exercise on trying to reduce that, finding the eddy losses with certain confidence, and so on.
Okay, thank you. Let's go to the next question. By how much did the temperature of the magnets decrease by implementing magnet segmentation?
Yeah, we do not have results of a thermal study within this slide deck, and therefore I'm not sure if I could give a correct answer in this range. Uh,
No problem. I think.
yeah, we have restricted ourselves mostly towards the e-magnetic sides, and therefore we most of our calculations are in those ranges. On a thermal scale, I believe we do not have the results as of now, but yeah, this is an interesting extension of our exercise, we believe.
Yeah, sure. Okay, thank you. Next question is, can you develop why you have choose this skew compared to a classical skew of one tooth pitch, or in case of PM machine, a stator skewing?
Fasil, can you take this question?
Yes. Can you develop?
Yeah, quarantine, can you repeat the problem
Yeah.
statement?
So
Yeah.
uh, when we select a SKU, there are an analysis we do to reduce the torque ripple and to bring the torque ripple to the requirement from EDU team or system teams, etc. So we have selected this particular set of SKU based on the consideration that the torque ripple should be below a certain level. So that is how we reach to this particular set of SKU. Hopefully that answers the question.
Thank you, Fasil.
Yeah.
I have a few other question. You take into account PWM in the drives?
No, we did not consider PWM effects in our simulation.
Okay, thank you. Maybe another one here. Give me 1 second. In the calculation of the whole 3D, did you include the N winding? Maybe the N effect would be bigger by including the coil N.
Currently, this model is not considering N winding. I understand there will be an effect of N winding, but that was not part of this part of the scope of this work.
Okay.
Thank you.
And maybe one last question. What is the calculation time for those 3D calculation? Did you use the flux gap boundary condition in GMAG?
Yeah, I think Yeah, the calculation time for 3D calculation for 3.5 stacks, considering a symmetric condition, and for one pole was roughly around, I believe, 5 to 6
Yes,
hours.
correct. That's right. And
And
for one
no,
stack, one pool, it was half hour.
yeah, it was half an hour simulation. And yeah, we did not use the flux gap boundary condition. We developed a model and missed it. Using the we missed the whole 3D model and ran our transient analysis on that, rather than extending it from a 2D transient analysis to a 3D frequency analysis, which makes use of the flux boundary gap condition in JMAG. We did it in a 3D transient analysis, transient magnetic analysis.
Okay, thank you for your answer. I think we have now covered all the questions. So I would like to thank you again for your participation to our user conference. So we're very glad to have you here. And I would like also to thank all the attendees for the question that have been asked. So yes, I think I will just conclude this session by sharing my screen very shortly. Okay, it seems there is a problem. I cannot share my screen, but I just wanted to inform you that there is a next session starting very soon in 1 minute about export of unprocessed GMAG field solution data for custom post-processing and visualization. So you can stay online with us and go to the next session, and also this afternoon we'll have more sessions. So have a very good day, everyone, and thank you again to the Jaguar and Land Rover team for their participation. Very nice presentation. Bye bye.
Thanks a lot, Quentin.
Yeah.
Have a great
Welcome.
day. Bye
Have
all.
a good day too. Bye bye.
Thank you. Bye.
Bye.